I guess the lab is kind of like the project.
I like projects because you learn from real world stuff, but too many, well, there's too many fundamental important things we got to get through, I guess, unfortunately. All right, well, I want to talk about, we're going to talk about a specific way that we make these filter plots today, but I want to review this concept, and I'm purposely not going full screen here for a second because I want to be able to flip over to MATLAB here in a second. So we talked about the basic idea of what a filter is, which is basically you look at the circuit, you get this H of S, right? So you basically replace your capacitors with what? Capacitors no longer C. What do we write for a capacitor?
1 over SC.
1 over SC, right? And SL for an inductor, all that sort of stuff. We derive the transfer function. Now, the transfer function is a function of S. But if we're only interested in what we call AC steady state, right? So AC steady state means if we have sine waves only, and we're only worried about the steady state, then in that case, what do we do with S? We set S equal to what? What do we set S equal to if we only care about sine waves? Hopefully you know this. This is what you've been doing on problems 3 and so in problems 3 and 4 on the homework, you set S equal to J omega, right? And then everything is the same. All right. I think that was the main point a lot of people were missing the other day was there's nothing different about what we're doing except S is J omega, right? That's the only difference. Otherwise, everything's the same. And again, we focus heavily on sine waves because they're a common type of input. We'll look at some examples here. But if I think about this, the other day I said, okay, well, if I have, the way we look at this transfer function is I say, I think of it as inputs and outputs. So inputs basically are the sources that are somewhere in the circuit, and the outputs are some voltage or current somewhere in the circuit. So what I've got here, this is what we looked at the other day. We said, okay, if I put in a sine wave at, what is the frequency of that guy in radians per second there? That cosine 10t, what's the radian per second frequency? 10, right? So it's 10 radians per second. So I look at the transfer function at that frequency, 10 radians per second, and I say, what's the magnitude of that thing? What's the phase shift of that thing? And then I can say that the output at that frequency is going to be what? Well, it's going to be the magnitude at that frequency times the amplitude of the input. And then the phase shift at that frequency is how much shift I'm going to get at the output. So if you look at this output here, right? So I put in something that had an amplitude of 1. This guy here, we said 1 over square root of 2 is basically 0.707. So the amplitude at the output is what? About 0.707, right? And the phase shift here, right? So this guy, so at t equal to 0, this guy was peaking. This guy peaks a little bit after t equal to 0. That's a negative phase shift, right? So the phase shift between them is negative 45 degrees. Okay. So basically what the filter transfer function does, or what the transfer function does, let me just take the transfer function. What that does is it basically tells us at a given input frequency, how much change in amplitude and how much shift does the waveform have. All right, now we'll look at where we would use this, right? We talked about this the other day, these general concepts of different types of filters. So low pass filters, band pass filters, high pass filters, right? So low pass filter does what? What is that figure that I drew there? What does that convey? It says,
it discards the higher frequency.
yeah, it discards frequencies above what we call the cutoff frequency. So it says omega C there. So above omega C, those things are filtered out. All right. Below omega C, they pass through, right? So if the input amplitude is 1, then the output amplitude is 1. That's the idea of a low pass filter, right? It just passes it straight through. High pass filter does the opposite, right? So high pass filter, the picture in the bottom, that says I pass only the high frequencies. And I try to, what was the word I use for when I'm not passing them? Attenuating them. Now, these are ideal pictures, what I've shown here, right? These pictures, what I call brick walls, right? Where what that low pass filter picture is trying to show is I pass everything below a certain frequency. And if frequency is above it, I don't get anything at all. That doesn't happen in the real world, okay? Instead, I make everything after the cutoff frequency smaller. I attenuate it. And then that middle guy I have is something we probably, well, we'll talk about those too, bandpass filters, right? Where you pass everything in a certain band, okay? Those are really common in radio. So one of the things I said too, if I look at a real filter has a transfer function. If I plot h of j omega like this, that's the magnitude of h of j omega. So remember, the transfer function is a function of a complex variable, right? J omega is what's in there. So that means the transfer function is a complex number. So I can't plot the transfer function. I have to plot its magnitude and its phase, or its real part and its imaginary part, because it's a complex thing. Usually we plot the amplitude and the phase because it relates directly to sine waves that way, okay? So what we said was, when I plot h of j omega versus omega, right? What I can see from this for a real filter, this is a real filter, what I've shown here, right? For this real filter, is that a low pass filter or a high pass filter? It's a low pass. Now it's not brick wall like I've got there, right? If I wanted to get closer to that brick wall, what would I want to do?
Doesn't it like need to decrease instantaneously?
Yeah, it would need to decrease faster. One of the things I said, we're going to deal more with this today, is if I make a quote unquote higher order filter, if I put more L's and C's into that filter, it will fall off faster. So these are two low pass filters, these two circuits here, right? The one on the right, or sorry, on the left. The one on the left is a first order filter, right? You know the term first order circuits. If I said first order circuit, what's a first order circuit mean?
It only got one storage element.
Only has one storage element. Now the one on the right is a second order because it's got two storage elements. That guy falls off faster. All right, you can kind of see that. These guys remain to have the same cutoff frequency, but one of them falls off faster than the other. Now we're going to deal with that question a little bit. So I wanted to try to motivate this a little bit. Again, I like the real world ideas here. So these are two audio signals that I have plotted in MATLAB here. They are two different audio signals. They're actually, the bottom one is, we're going to listen to it in a second. The bottom one is a little snippet that is built into MATLAB, but it's Handel's Messiah, basically, if you've heard that before, right? It's a little choral thing. The top is basically a noise corrupted version of that, okay? If I asked you, I want to get the bottom signal out of that thing, but what I'm given is the top signal, which is, there's got noise in it. If I listen to the noisy signal, let's listen to it. So hopefully you should be able to hear it. All right, so I'm going to do in this. Okay. That sounds
Like a broken lightsaber.
like a broken lightsaber. Okay, maybe. That it sounds nasty, right? If I play this is the bottom one. Now you could probably. All right, so that's very clear, hopefully. All right. You can hear that same audio signal inside there, but it's being distorted. So this noisy, distorted thing is the one on the top. The one on the bottom is the one that sounds clean, okay? If I said to you, turn bad on top into good on the bottom, what would you do?
High pass filter.
How do you know that?
Because the one at the bottom, the frequencies that seem most clear are.
Well, okay, okay.
Focusing on certain frequency.
Well, I would say I look at that and I don't know what the hell's going on, but you got the right answer. All right. Well, so frequencies are on the time axis. I just see a big blue blur there, right? If I look at this, so one of the things I can do, this is why the frequency domain is important. This is the time domain, right? If I want to know what's really in a signal, there's tools you'll learn maybe in 2254 about, if I look at this, I can look at this somehow in the frequency domain. So what I did here is I plotted something called the Fourier transform of that signal. And basically what I'm showing on the y-axis here is the phasor magnitude at each frequency in that signal. So what this does is it looks at these signals, right? It looks at these guys. Oh boy. I guess those plots are big. All right. It looks at these signals and it says, what are the frequencies in there and what's the phasor at each of those frequencies? And so what I've got here on this slide is that's the noise right there. I got a noise at 60 hertz that's really big. All right. So if I wanted to get rid of that, what should I do? I should do a high pass filter, right? Or maybe a band pass filter. You could maybe do that too, but it doesn't look like there's much meaningful stuff down here, does it? It looks, this stuff here, these are all the frequencies that are in that song, right? And what I was trying to do is say, I want to get rid of all that stuff and I want to design a high pass filter that passes this stuff and gets rid of this. Okay, makes sense. All right, that's the whole idea of what we're doing when we do filters, is we're trying to get rid of the things we don't want and try to keep the things that we do without screwing up the signal. And you can screw it up if you do your filtering wrong.
So for the one that we just listened to,
Mhm.
the peak at 60, is that
That's the noise that's somehow in that signal. What's that?
was that like the noise of the whole thing? Like,
Yeah. So if you looked at this, right, the top signal, this is the noisy one. So you can kind of see, like, there's these sort of, in the time domain, there's these spikes. You can see them coming through here, right? There's a 60 hertz that's added on top of this. And that's a common buzz. You may have heard like a microphone, somewhere in like a public address, and you hear that kind of, that's a 60 hertz somehow hum. You could have all sorts of them, yeah. Yeah, and we can get into all kinds of things. What if they overlap? And there's all sorts of problems that can happen, but I just wanted to get the basic idea across here, right? All right.
So the first one is just no filter at all.
The first one is no filter. The bottom is filtered out.
So if I were to use the low pass filter, would it amplify the static noise?
Well, if I used a low pass filter, it would have just left, depending on the low pass filter I made, right? Let's say I made a low pass filter that went like this, right? So it was passing just that stuff. I would have just heard bzzz, and I wouldn't have heard pretty much any of the music. Okay. But you can hear it works pretty well, and filters are used for everything. All right. So now I want to go over into my full screen. Nice, this stupid thing. Okay. All right, and I got to fight with PowerPoint. All right. Okay. So I'm going to pick up with where we were last time. I talked about sort of another example. I said, what if I had this PV inverter, right? So I had photovoltaic or solar panels connected through some power electronic device that takes the DC output of that solar panel and connects it to the grid. And I said, what happens is if Duke Energy does not want there to be a lot of noise going on to their grid. They want 60 hertz currents on their grid, right? And so the output of this thing, I sub L, what I said is I sub L looks like what I have written out here. It will look like a nice 60 hertz current plus a lot of noise. And that noise looks like what I have shown up top to give me a total waveform which has a 60, so this I sub L at the bottom, right? This is my I sub L. It's noisy, but it has the 60 hertz inside of it, okay? What the requirement that the utility places on me as the guy who hooks up my solar to the system is it says, get rid of that noise before you hook up to our grid. So you are thus required to put in a filter. So in this case, we put a filter in that says I sub L is my input, I sub G is my output. And I want to make sure that I sub G is much closer to just this 60 hertz here that is underlining this guy. Okay. I want to try to just get that and get rid of the junk on top of it. Okay. So basically what that says is there's two signals in there. One of the signals is at 100 kilohertz. All right. So 2 pi times 10 to the 5th radians per second. And the main signal is at 2 pi 60 radians per second. And so as a filter, I sub L is the input, I sub G is the output. Okay. If I look at that thing right there, I'm going to have a transfer function. So my transfer function, I sub G over I sub L is H, right? And so in this case, what I'm saying is my goal is to have a magnitude at 60 hertz that's equal to 1, right? And a magnitude at 10 to the 5th hertz that's equal to or less than 0.01. All right, so think, what does that mean? At 60 hertz, I want the amplitude to be 1, which means what? I'm passing that, right? It just goes right through. To say that I want the magnitude to be less than 0.01 says that I want what? I want to filter it, and I want it to be 1% of whatever I had going in. So I want to multiply it by 0.01. That's 1%, right? So I'm going to make it a lot smaller than it was before. Right. So as a designer, I need to design that filter. Well, let's say if I was the designer, I designed the filter that I have right here. All right. So there's some superposition and stuff going on because the grid's a voltage source. So let's just think of this thing as I have a capacitor and I have I sub G over here in this inductor. This is L2 and this is C. All right. Here's I sub G. And I sub L, even though there's an inductor over there, I already know what that current is. I told you guys what that current is, okay? So if I needed to find out I sub G and I know I sub L, how would I figure out that H of S from that picture? Current divider, okay? I do a current divider relationship. So we'll say it like this, okay? I would say my input is I sub L, so I sub G, if I do my current divider relationship, is going to be I sub L. So it's the voltage across them, right? Divided by the impedance in that branch. I know you guys sort of know that becomes 1 over SC divided by 1 over SC plus SL2.
Did we turn off the grid?
I turned off the grid, yeah. I'm doing superposition to figure out what it's going to look like.
Okay.
Right. So if I want to get my transfer function is that guy that I wrote right there, right? This thing right here. This is H of S. Okay. So how do I get that into a nice rational function of S? Multiply everything by SC. Okay. And this thing, I'm going to find that my H of S is 1 over 1 plus SC S squared L2, like that. All right. Now, that guy has how many poles?
Poles would make the numerator 0, right?
2 pole.
2 poles. 2 poles. Tone for the win. Yeah. Yeah. So poles are the things that make it go infinite, right? So that means the denominator equal to 0. Think of the pole, really big. 0 is 0, right? So numerator, whatever makes the numerator 0 is a 0. Whatever makes the denominator 0 is a pole. All right, so this guy's got 2 poles. All right. Now, let's say I plotted H of j omega for that guy. So I plotted the magnitude of H of j omega. That is a weird looking plot, isn't it? That's the plot for that guy. What does it say? It says this guy is enormous at some spot, right? And then he is relatively small, right? After that. Is he constant? He's not actually, right? It looks like he's 0 for sure, right? Doesn't it? I mean, it looks like it's 0. Thing is, it's actually not 0. And this is a problem. I have something on this graph that is 7 times 10 to the 4th and I have something on this graph that's like 0.01. That's a hard graph to look at. Anybody know how I would try to look at that? This is a very common problem. What is a way to look at that kind of thing so that I could see everything much better?
Put it into log scale.
Put it into log scale. Who said that?
I said it.
All right. All right. Parker knows a little bit about where we're going with this. Yeah, we put it on a log scale. Log scales help us zoom in. And so this is a pretty common issue. So if I had the number X, so I did a couple of ranges here. Let's say I wanted to show everything on the same graph from 10,000 down to 0.001. Showing that on the same, that's what's going on here, right? Basically I have 70,000 and 0.001. It's hard to see them together. If I take the log, that fixes it. Okay. What's the log? All right. So we're going to start to remember logs here, right? So what's the log of 10,000 or 10 to the fourth?
4.
4. Yep. 4. What's the log of 1,000? 3, 2, 1, 0, -1, -2, -3. Now, 10,000 and 0.001 are what? This is 10 to the fourth, and this is 10 to the -3. They're 7 orders of magnitude apart from each other, right? That's a big distance, right? 4 and -3 are 7 numbers apart from each other, right? They're a lot closer together. So when we take the log of it, I get that, right? So the thing on the left is the original plot of the magnitude. What we do instead is we plot the log of the magnitude and we plot it versus the log of frequency. That plot has a special name called the Bode diagram or the Bode plot. All right. And so that's what this is here, right? And some of you guys have probably heard the term before, Bode plot. You've probably also heard the term decibels before. All right. So we use decibels as the unit on the y-axis for the magnitude. And for reasons I don't want to describe, you would think we would just look at the log of the magnitude, but no, we made it hard. We look at 20 times the log of the magnitude. Why? Some historical reasons, all right? But they're not all that important. We look at 20 times the log of the magnitude, all right?
For the y-axis.
For the y-axis. All right, so we're always going to do 20 times the log of the magnitude. We could look at the log, and the whole idea was to look at the log, all right? But some guys at Bell Labs back in the 20s, right, decided we were going to look at 20 times the log, all right? And so it goes, all right? That's basically what was decided.
And both of these graphs are mathematically equivalent.
Both of these graphs are mathematically equivalent, but now I can see, so 10 to the 5th is here. I can see it pretty clearly. And 60 hertz is on this graph as well, right? So I can see all kinds of crazy stuff going on in this graph. All right, so these two things are showing me the same thing. It's in general. Anytime we look at stuff electrically, we look at 20 times the log. Okay. So if I look at this thing, so if I want to know what's going on, so I was putting in something that had 60 hertz and 100 kilohertz. Okay. So what I did was I looked at those frequencies. So 2 pi 60 is approximately 375. It's actually approximately 377, but 375 is close enough. And 100 kilohertz is basically about 629 times 10 to the third radians per second. So what I do is I look at this chart and I say, well, what's the magnitude at those points? So here we are. Here's my 60 hertz right here. All right. And what it says is the magnitude is 0.00123. So what I say is 20 times the log of the magnitude at that frequency is equal to 0.00123. So how do I figure out the actual value of the magnitude at that point? How do I figure that out?
10 power.
What's that?
So 10 power to.
Well, so yeah, so I'm gonna multiply. I'm gonna divide both sides by 20 first.
21st, yes.
Right. So I'm gonna have 0.00123. The combination of my luggage. All right, divided by 20. All right. So I got the log of that number is equal to that. Now, if I have the, so what Tone correctly identified, right? If I have the log base 10 of x is equal to some number, right? Let's say n. How do I solve for x?
X equal to 10 power.
Exponential.
Yeah, you raise both sides to the power of 10, and this thing becomes x equals 10 to the n, like that. That's how you undo the log operation, right? So in this case, what I would say is I would raise both sides of the power of 10, and I would say the magnitude of this guy is 10 to the power 0.00123 divided by 20, like that. Okay. All right. And what does that become?
It's pretty much 1.
Pretty much 1. Okay. So that says that the magnitude of the transfer function at 60 hertz is 1. That's what we wanted, right? So this guy has a magnitude of 1 at 60 hertz, which means it's doing what at 60 hertz? It's passing it. Okay, it's passing it through. Now, then I have, okay, well, what's going on out there at 10 to the 5th? Well, it's different, right? On the previous graph, it was impossible to see. You would have said it was 0, right? Well, when I look at this here, out at that frequency, 6.29 times 10 to the 5th, I go out there, I see that the magnitude is negative 51.9 decibels. All right, so what do I do to figure out the actual magnitude? 2 steps, right? Divide both sides by 20, raise both sides to the power of 10. So it becomes the magnitude of h of j 2 pi 10 to the 5th is 10 to the negative 51.9 divided by 20. Do the math on that, it's about 0.0025. Okay. That means that the output of this filter at that frequency is going to be 0.25% of the input, right? Is what it means. Okay. That's a good thing. It means that this thing, this noise that I had that was apparently going from minus 1 amp to 1 amp is going to become what? So if it's minus 1 here to 1. So it's going to be, instead of 1 amp to minus 1 amp, it's going to be 2.5 milliamps, right? Is what it says. It's going to be 2.5 milliamps to negative 2.5 milliamps is what's going to happen. You guys follow that? That's the basic idea, all right? And so to say that it's, is that 0? It's a lot smaller. But if Duke said, hey, you got to make sure that current's less than 10 milliamps at that frequency, I can't just say, well, it's almost 0, right? I need to say, no, it's 2.5 milliamps, right? So there's a reason why we need to not just approximate, but we need to know what is the true amplitude. And the log really helps us to do that. Yeah.
So basically, you're shortening the amplitude, right? That's basically.
Yeah, I'm reducing the amplitude at those frequencies. And it's hard to see that reduction that's happening if I look at a linear scale. So we look at a logarithmic scale instead. Okay.
This doesn't mean that the amplitude of that signal is 1. This is just a transfer function which you would multiply by.
Yes, this is yeah. So at 60 hertz, I multiply the input amplitude by the transfer function, and it becomes, in this case, I think the 60 hertz component was 2 amps. Peak to, well, 2 amps peak. So the output would be 2 amps peak, right? But the noise, which is 1 amp peak to peak on top of it, it's going to become 2.5 milliamps. Okay, it becomes much smaller. All right, so that's our basic idea. Now we got to figure out how do we actually make those Bode plots, because there's this is one of those things that living in an online world where I'm not going to focus as much on this as we used to because you guys are going to be able to do this in MATLAB at home when you take the exam, and making the plots by hand isn't going to be all that important, but I want you to know how to make the plots by hand, because it is important because we talk about, well, what does a pole do to the magnitude? What does a zero do to the magnitude? You need to have some intuition about that. All right, so here's the thing. You are going to get transfer functions from circuits. So you're going to do circuit analysis. You're going to get transfer function. It's going to look in general like this guy. Okay. So it's an ugly looking math thing, right? This has been math week, right? We've had some ugly math, right? This is kind of where it ends. And this is probably the last day of ugly math that we'll have in the semester. All right. In general, what this guy looks like is he's got a bunch of poles and zeros, and they could be factored out. So what I've done is factored out into a bunch of what I call first order poles and zeros, right? So what I have here is this guy here, K, he's a multiplier on the whole thing. And then I have poles and zeros at the origin. What does that mean, poles and zeros at the origin? What do I mean, the origin? In other words, S, if I have S in the numerator, S in the numerator means I have a 0, right? And where is that 0?
Origin.
Well, yeah, it's at 0. So it's at the origin when I draw that picture of the poles and zeros.
So is that like an initial condition?
No, has nothing to do with that. It's just a pole. It's a polar 0 at the origin, right? Which means that somehow something about that circuit means that it has a polar 0 at the origin. Op-amp circuits give us that a lot. All right. And so this guy's got a bunch of poles, bunch of zeros. I'm trying to think of it in general. In general, our transfer functions have this shape. And we're going to say, okay, if I have a transfer function of this shape, how do I draw that Bode plot? How do I draw that thing that looks like this? All right. I want to know how to make that drawing. So, all right, let's take a look at sort of an example transfer function here. So I've got this guy here, 10 to the minus 4s, okay, over 10 to the minus 5th s plus 1. And I want to define what is the k value. What's that? So in other words, in that general form, what's the multiplier and where are the poles and zeros? Okay. So looking at this thing right here, what are the values of s that make the denominator equal to 0?
So 1 over 10 to the 5th.
1 over 10. So and I should be careful. It's negative 1 over 10 to the 5th. And that has units of radians per second. All right. So that's at a particular frequency. So that means I draw a little x out here at negative 1 times 10 to the 5th. Sorry. Negative 1 over 10 to the minus 5th, or 10 to the 5th. Okay. Now, that is my pole. Sorry, I put that in the wrong spot. Right? My pole is what makes the denominator equal to 0. Okay. Where are my zeros for this guy? 0. Okay. He's got 0. So he's got 1 pole and 1 0. What's the multiplier on this guy?
1.
Not 1.
10 to the negative 4.
10 to the negative 4th. Right? So we said in general, this guy, there's a multiplier in front, right? So the multiplier here is 10 to the minus 4th. It's multiplying the whole transfer function. Okay.
So in our transfer function, S always has to be by itself on top. Not always, but
So our transfer function always has to get into that form. All right. We're going to see an example today, and we're going to do more examples next week where we do this. But we got to get our transfer function into this form. Because your transfer function, when you do straight up circuit analysis, may not end up in this form. You're going to get it in this form to be able to make those plots. Okay. All right. So we look at a transfer function, we identify the poles and the zeros. And then we figure out, okay, well, once we know those things, we figure out how we construct the Bode plot. All right. So we've talked about this for various circuits, right? So my favorite circuit, V out, so RC circuit, V in and V out. I get this transfer function, right? So how did I get that transfer function? Voltage divider, right? Voltage divider gives me that transfer function. And if I'm worried about sinusoidal steady state, my jump is to let S equal J omega. Okay. All right. So I'll look at an example circuit. He's going to be my example that I use going throughout here. So I got a 1 kilo ohm resistor, 1 microfarad capacitor. All right. Pretty standard values for a breadboard type of circuit. All right. So this guy right here, where's his zeros? Do you have, yeah, that's right. Where's his zeros? Does he have zeros?
No zero.
No.
No zeros. Does he have poles?
Yes.
Yeah, where's his pole?
1000.
Negative 1,000.
Negative 1,000, right? Negative 1 times, so 1 over 0.001 is negative 1,000, okay? So negative 10 to the third radians per second. I want to figure out how to draw that Bode plot for this thing. In other words, I want to draw the magnitude of h of j omega on that log plot, okay? So I want to figure out how to do that. So to do that, I'm going to think through two things. How do logs help us make these plots, right? There's two reasons, right? You can make really simple approximations about a single pole or a zero, right? Which we're going to show here in a second. All right. Now the second piece is this idea here. The log of a product is the sum of the logs. So I already wrote it out there on the screen. If I have the log of AB, so the log of a product becomes the sum of the logs. You might have seen that. You should have seen that at some point in high school, right? You also maybe saw that with Yahoo in 2254. Not sure. All right. Yeah, I don't cover logs much there either when I do it. Yeah, but it's a, you know, it's an important thing. Why is that important? Well, because if you look at my general form here, what do I have? I have products of things. So if I take that log of that whole thing, then it's going to become the sum of the logs of each of those things. That's going to turn out to be helpful to me. Okay. All right. So we're going to use those two facts here a little bit as we go through this. All right. Now I also put in a log of A over B. Right. If I have the log of a quotient, right, then I subtract those two things. All right. So we'll look at this guy here. So I had h of s is 1 over 0.001 s plus 1. That was our example. All right. And I plug in s equal to j omega, and I get this guy here. Okay. So what I have is basically the situation where I have 1 over j omega tau p. So tau p, I'm going to use this term tau p. Tau is a time constant, right? We use the term tau for time constants when you learn first order circuits. That tau is 0.001, okay, like this. So what I do is I take a look at that expression right there, all right? So if I guess I have it written out, but I guess I'll just to go through it slowly, right? Negative 10 log of 1 over the square root of, so the square root, so the, okay, let me make sure we follow this. Here's my h of j omega right here, okay, like that. If I take the magnitude of that thing, how do I take the magnitude of that? So the,
Magnitude of top divided by magnitude of
yeah, we'll do it. Well, so let's say, but I want to do it as I don't want a number. I want a function of omega, right? So we have to do it the men were men way, right? So it's the magnitude of the top divided by the magnitude of the bottom. What's the magnitude of the top? 1. What's the magnitude of the bottom? All right, somebody online.
square root of 1 plus 1 square plus 2 omega tp square.
All right. So 1 plus omega squared tau p squared, like that, right? So I took the imaginary part squared, the real part squared. Real part's just 1, right? So what I want to do is I want to take the 20 times the log of that, right? So what I have is 20 log 10 of 1 over 1 plus omega squared tau p squared, like that.
Shouldn't the j squared equal -1, so it would be a minus?
This is the problem with MATLAB, right? So when I look, so if I have real, what's the imaginary part of that number?
Like 0.001.
No. Well, yeah, omega, so 1 plus j omega times 0.001, what's the imaginary part? It's the coefficient on the j. The j is not the imaginary part, right? The coefficient of the j is the imaginary part, right? The j is not part of it, right? So it's always,
So I don't square j when I'm doing magnitude?
no. You take real part squared plus imaginary part squared. The j is not the imaginary part. The coefficient of j is the imaginary part. All right. So I get this guy here. Now what I do with that is I say, well, I can break that up like this. 20 times the log of the top minus 20 times the log of the bottom. Okay. What's the log of 1? 0. So that guy goes away. So I'm left with just that term. Okay. Now, what I want to do is I'm going to look at that. I want to look at that term for a second. Okay. So looking at that term, I'm going to talk about basically an approximation for trying to deal with this thing. So we're going to do classic engineering thing, right? Engineers don't like to do math, even though that sounds like a strange thing. You guys laugh because you're like, well, all you guys make us do is math. Well, that's true. We make you do a lot of math. But for the most part, we don't like to be mathematicians and get too detailed about this. So what I want to say is I want to make some approximations on this thing. I want to look at 2 frequency ranges. I want to look at low frequencies and I want to look at high frequencies. Now, somebody made the observation last class about what's low and what's high is all relative. Right? It's relative to what? Well, what would be our reference in this case, you think? Let me give you the hint. Let me say, let's look at omega tau p much less than 1. Okay. All right. So in other words, that means so that's an engineering thing to do. 2 less than signs, right? Which means much less than. What does that mean?
Is 1 a reference?
No. Let me finish.
0, basically.
Well, yeah, it means 0. Usually means like at least a factor of 100 different, maybe, or a factor of 10 different, right? So that tells me I can write this as omega much less than 1 over tau p. Right? I just rearranged that expression. So that says I'm looking at frequencies much lower than what I call the pole frequency. All right. So if I look at my example circuit here, this guy had a pole at 10 to the 3rd radians per second. So at a frequency much less than that, I can make an approximation for this thing. Okay. So if I look at that expression that that -20 log 10, whatever, if I look at that guy for omega tau p much less than 1, what's true about the argument under that radical there?
1.
Yeah, if omega tau p is much smaller than 1, basically this guy becomes just approximately -20 log 10 of 1, right? In other words, I got 1 plus a number much smaller than 1. 1 plus a number much smaller than 1 is 1, right? If I take the square root of 1, it's 1. So basically this guy is equal to what? What's 20 times the log of 1? 0. 0. Okay. All right. Now let's look at the other extreme. What would the other extreme be, do you think?
Much
Much greater. Yeah, much greater. Yeah. Omega tau p much bigger than 1, which says that omega much bigger than what? 1 over tau p. Like that. Okay. All right. So in that case, how do I approximate that? Well, not infinity, but which term dominates there? One, I have one plus previously I had one plus a small number. We said that was one. Now I have one plus a big number.
Remove one.
Big number, right? One plus big number is big number. One plus little number is one. All right, it's basically a very caveman-y sort of statement, right? Right, one plus big number, big. All right, so I'm going to say this guy is approximately negative 20 log 10 of what?
1 plus
Well, it's
number.
omega, it's just this guy, right? It's approximately that. I got rid of the 1. Okay. So square root of a square is what?
Just whatever's in there.
Whatever's in there. So it becomes omega tau p. And then I can break that up saying that's negative 20 log base 10 of omega minus 20 log 10 of tau p.
Shouldn't it be plus?
Nope.
Negative 20 up front.
Negative 20 up front. Yeah. All right. So let's blow our minds for a second. All right. So if I look at this thing, this guy here is like a linear function. Okay.
Sorry, Dr.
Yeah.
Why'd you split that up?
Why did I what?
Why'd you split up that negative 20, log 10?
Well, so if I have log of two numbers multiplying each other,
Okay,
I can make that the sum.
okay.
Okay. So if I look at this for a second, tau p is going to be a number that we know. In my example, it's 0.001. We're going to go back to that example in a second. This guy is a constant. This guy is a function of omega. On a logarithmic scale, I can think of this as my x variable. And I can think of my magnitude as my y variable. So in other words, it's like I have some function that is y equals negative 20x plus b, where x is equal to the log of omega, and y is equal to 20 log of the magnitude. Like that. The magnitude is 20 log, right? But in this particular case, it's become negative 20. All right. This is going to get very simple in a moment. It looks complicated now. It's going to get very simple, right? What does that say? Well, what this says is for low frequencies, the magnitude is constant. For high frequencies, it says that the magnitude falls in a linear way on a logarithmic scale. All right. Linear way on a logarithmic scale. All right. And so we can make some nice approximations from that, which is what we're going to do. Okay. So let's look at an example of how we try to deal with that. All right. So let's go through. Example always helps us. So what I've got here is what I call log paper. All right. So effectively, each of these ranges here is a factor of 10 in frequency. And we call a factor of 10 in frequency. Anybody know what the name for a factor of 10 of frequency is? It's a decade. All right, is what we call it. All right, a decade, just like, you know, the 90s or the 80s or whatever, right? It's a decade, right? So it's a factor of 10 in frequency. All right, so if I take this, my original example here, what I said for my original example, 1 over j omega 0.001 plus 1 becomes this guy. When I plug in everything, take the magnitude of the top, take the log of that, multiply the log by 20, I get that expression. Okay. Now, what I want to do is I want to make a plot of this thing on those axes right there. Okay. Now, what I've got there, so I've got this little table to help me out. I said for different values of omega, I want to just kind of dimension up the axes for a second. Okay. So what I'm going to do is, so these guys are weird. So if you looked at this, this would be this point right here. Well, let me go slowly. Omega is 0.01, omega 1, omega 10, 100, 1,000. Okay. So what we were saying before, right? If I take the log of 1, what number do I get when I take the log of 1? 0. Log of 0.1, I get -1, right? So what it says is on a logarithmic scale, if I take the log of a bunch of numbers that are separated by a factor of 10, they become what? They're separated by an order of magnitude normally on a linear scale. But on a logarithmic scale, those numbers that are separated by a factor of 10 are separated by how much? Yeah, they're linearly separated now, right? By a factor of 1. So I'm gonna say that this point right here is 0.1 radians per second. I'm gonna say this point right here is 1 radian per second. And so this guy would be 10. This guy would be 100. This guy would be 10 to the 3rd. This would be 10 to the 4th. And this guy would be 10 to the 5th, right? Think about it. This guy is -1, 0, 1, 2, 3, 4, 5, right? So they're separated by a factor of 10, okay? But effectively linearly spaced on this, okay? So what about the y-axis? What would I do there? Well, I would mark off basically this guy is going to be 20 dB. This guy will be 0. This will be -20 here. This will be -40. This will be -60, like that. Yeah, it's because of the fact that it's 20 times the log. Yeah, so if I was doing it, it would have been right 10, 0, -1, -2, -3, so on and so forth. But because I have that stupid 20 in front, it becomes that. Okay. All right. So we've dimensioned that up. Now what I want to do is I want to make a plot, and I want to. Is there a way? Ooh, I didn't want to do that. Crap. Can I undo? I can't undo that, probably. Shit. I wanted to keep that. All right. I don't know how to change. Is there a way to change the colors when I'm in full screen mode? Crap. Come on. All right. So this was 0.1. Oh man. 0.1, 1, 10, 100, 1,000, 10,000, 100,000. And this was 20, 0, -20, -40, -40, -60, -80, like that. Okay. So what I want to do, can I change colors? Maybe not. All right. What I want to do is I want to use that approximation we made here, right? So we said for frequencies much, much lower than the pole and frequencies much, much higher than the pole. Okay. What's the pole here?
The pole is 1
over 0.001 and omega much, much bigger than 1 over 0.001. Okay. So for frequencies so it turns out we don't need to do much math at this point. For frequencies much, much lower than that pole, what was the approximation we made?
0.
It's approximately 0. Okay. So where is that? Where is 1 over 0.001 on my graph here? No, 1 over 0.001. So 1 over 0.001 is
-1,000, I think, because you forgot the negative side.
There's no negative sign, right? It's 0.001.
It's a 10 to the 3. You know what I'm saying?
Well, so 1 over 0.001 is 1,000, right? So 10 to the third. So that frequency is right here, right? At 10 to the third. So for frequencies much, much lower than that, where is the magnitude? It's at 0, right? So it's basically here along this line, right? Now, for frequencies much, much greater than 1,000, what did we say it did? Yeah, I lost it, right? Frequencies much greater than 1,000, what happens? I said this guy became approximately negative 20 log 10 of omega minus 20 log 10 of tau p, like that, which I said is sort of like y equals minus 20x plus b, where x equals log 10 of omega. So we said is on a logarithmic scale, that thing is what?
Fall.
It's a line.
It's a line.
Yeah.
So, and it's a line with a slope of what?
So b over negative 20.
The slope is negative 20,
Negative 20.
right? The slope is the multiplier on that x. So basically what it says is for frequencies above that point, I fall at a rate of negative 20 decibels every factor of 10 of frequency I go. So if I go another factor of 10 in frequency, I fall another negative 20 dB. The question is, how do I decide much, much greater than and much, much less than? Let's say we don't want to. Let's just say we're going to approximate that much, much less than goes all the way up to that point, and much, much greater than begins right after that point. So I'm going to say, and I'm just going to make that up, and we're going to see if it's a reasonable choice, right? So that means that in the decade that goes from 10 to the third to 10 to the fourth, what's the magnitude going to do? From decrease 20. So I'm going to get to negative 20. And then by the time I get to 10 to the fifth, where am I going to be? Negative 40. So I'm going to fall like that. Okay. And this slope here, I'm going to say is negative 20 decibels per decade. All right. And so it tells me that the magnitude is falling after the pole. Okay. Now, I made that approximation that I could just draw those straight lines. So I went into MATLAB and I said, okay, well, MATLAB, what does it actually look like? If I said, plot for me, MATLAB, negative 20 log 10 of the square root of 1 plus 0.001 omega, plot that. Don't make an approximation, just plot it. If I do that, what I get is that blue curve. And what I just did with my approximation was that black thing. They're pretty close to each other, okay? And in fact, I can figure out what's the maximum deviation. The maximum deviation here is right at that frequency, right at the pole frequency. I'm going to call it omega p. All right, omega p is 1 over tau p. Right at that frequency that corresponds to the pole. Right at that frequency, the magnitude at that point, if you plug in everything, you're going to see this guy becomes negative 3 dB. All right, so sometimes that's called a negative 3 dB frequency, right? And that term is something some of you guys might have heard before, right? At that point, the maximum difference between my approximation and the actual is minus 3 dB. All right, the bottom line for that is that essentially it tells us this. I don't need to know a whole lot, right? Basically, it says if I know I have a pole, all right? If I know I have a pole, the log magnitude is 0 for frequencies lower than the pole frequency. And the log magnitude falls at 20 dB per decade for frequencies above it. All right. For frequencies below a pole, my magnitude is constant at 0. For frequencies greater than the pole, my magnitude drops at 20 dB per decade. If I did the same analysis for a 0, I'd find the opposite thing. Right? Instead of having a negative slope, because it's on top, it would have a positive slope. And so what I find is the log magnitude is 0 for frequencies lower than the 0, and it's rising at 20 dB per decade for stuff greater than that frequency. Okay? And that result is important, but I basically have this other thing is to say, well, if I have this ugly transfer function, it's just ugly, right? It's in this form, right? If I take the magnitude, if I take this guy right here, and I take the magnitude of all of those individual components, it's that ugly expression right there, right? All those square roots, all this stuff. But if I take the log of that, it simplifies itself, right? It becomes the log of this constant plus the log of this guy plus the log of this guy plus the log of this guy. And I have all of these terms that kind of come into play. Why would that be important to me? Without going into the details, why would that be important? Anybody know? Why would that be useful?
You can analyze each individual
You can
component.
analyze each individual component and you can add them up. So what we said is, so what we just showed is how to deal with one component, right? If I know how to deal with one of them, I can deal with each one individually, and then I can just add them, right? So it's very easy for me to look at the result of a single pole or a single zero and just add them all up sort of piece by piece by piece to create the whole diagram, okay? So the process becomes pretty straightforward, okay? We're tight on time, but let me see what we can do here. All right, so there's a special case too where I say, well, so I can have a zero at the origin or a pole at the origin. All right, so if I have a zero at the origin or a pole at the origin, then what happens is the magnitude for a pole, then the magnitude falls at all frequencies. All right, and for a zero, the magnitude rises at all frequencies. All right. And what I showed here is that this guy crosses through zero. This should be kind of obvious, maybe once you look at it. At what point, if I take the log base 10 of omega, or 20 log base 10 of omega, when omega is equal to 1, is when this guy is equal to what?
0.
0. Right, so this guy's crossing through 0. This is the 0 dB line in the middle, right? He's crossing through the 0 dB line at omega equal to 1. Okay. So, all right, so basically what it comes down to is to be able to make these plots, you need to be able to understand these rules right here. And you need to be able to understand these two rules right here, right? The magnitude rises for all frequencies for a 0 at the origin, and it falls for all frequencies for a pole at the origin, okay? Now, given the time we're at here, so we're at 3:38, all right, I'm not sure if we're gonna have a whole lot of time to do an example here today, but we're gonna talk about examples all class on Monday, basically, and try to use this. So basically what there is there's 5 steps here to this process, okay, for making this thing. So basically what you do is you determine the pole and 0 locations. You look at that transfer function, you find those pole and 0 locations. And then I have this step 1A, which is to determine the corresponding breakpoints. I'm going to talk about that in a second, right? But I find the pole and 0 locations. Then I need to get the transfer function in the correct form, right? He may or may not be in the correct form. He'll be close to that, right? But I can easily get it there. Then what I can do is I can generate a plot for each individual pole and 0, moving from left to right. So what I do is left on the frequency axis, right? What's left? That's low frequencies, right? As I move from left to right, I'm going from low to high. Okay. And if I have a pole, I'm going to say it's equal to 0, and then it's going to fall. If I have a 0, it's going to be 0, and then it's going to do what? Rise. Okay. So what I do is I say, all right, I do each individual polar 0. And then what I do is I combine them all. So moving left to right, I add all those results. Okay, I put them all together. And then what I do is I shift everything up or down based on the K value, right? So if you look at that K value, that multiplier in front, right? Log of a constant is just going to be a number for all frequencies, right? So that guy is either going to shift the whole thing up or down. All right, so this turns out to be a really easy process. It looks complicated at first, but it turns out to be a pretty easy process. All right, so let's start with an example here. I have this guy, which comes from an op-amp circuit of some kind. All right, first question is, I want to determine the pole and zero locations for that guy. That's step one. All right, and then I get the breakpoints. All right, then I got to get, okay, so let's go through this. Determine the pole and zero locations. So what are the pole and zero locations for this guy? What's a pole?
Anything that makes the denominator.
Anything that makes the denominator equal to zero. So where's my pole here? Somebody
Neg-
online.
Negative
10 to the 5th.
Negative 10 to the 5th. Okay. And where's my zero? Oh, I did.
Zero.
Yeah. Negative 10 to the 5th. All right. Where's my zero? It was a 0. I heard Steven say that. Okay. All right. Now, that looks good. So that means this guy, I got a 0 here, and I got negative 10 to the 5th here. Now, the problem is, and I think Tone already said that, Tone's like the Secretary of State for the class. He sort of stands, he's my mouthpiece out in the world. So if I look at this whole thing, determining the corresponding breakpoints. So one of the things that like Tone kind of indicated, I think in his question, this pole has a negative sign, right? Because it clearly is a negative value of S that caused the denominator to become 0, right? We're not talking about negative frequencies. Once I go into the J omega piece, what ends up happening, and this is always kind of confuses people, what ends up happening a little bit is that the actual change points on that graph, when I plot the magnitude of H of J omega, the change points happen at positive numbers that correspond to those poles and zeros. So what I do is I call those break points, because they're the points where that graph breaks, where it was flat and now it falls, or it's flat and now it rises. We call those break points because that's where it's breaking, it's changing, right? So what I do is I come up with break points, and I say the 0 frequency is at 0, and the pole frequency is at 10 to the 5th radians per second. All right. It's just because of the math here, there's just a relationship. The actual S values are negative, but the frequencies they correspond to are positive frequencies. It didn't. It was 10 to the 5th, right? 10 to the 5th, yeah. Yeah.
So the breakpoint is essentially.
The breakpoint's basically just a positive number, whereas it's always going to be positive. Always going to be positive. And again, it's just a definition that we make, and it relates to the fact that the values of S are negative, but once we plug in S equal to J omega, we take the magnitude of that. Things happen for the positive frequencies that those things correspond to.
So can I think of my breakpoints as the absolute value of my poles?
You can think of it that, yeah.
Okay.
Right. Yeah. So, all right. Step 2 is to get the transfer function in the correct form. How do I do that? Is that guy in the correct form? So there's the correct form on top. All right. So that in this case, I wrote that very generally, but in this case where I got one pole and one zero, it should be K times S over S tau P plus 1. Right? It should be that. Is that guy in that form?
Yes.
No.
K equal to 1.
1/10.
What's causing so there's a problem here. What's causing the problem? The 10 to the 5th, right? He's not quite in the right form. So I need to factor a 10 to the 5th out, don't I? So
I see.
so I have S over 10
10 to the
times 10 to the 5th, right? Times S over 10 to the 5th plus 1. Like that. Now that guy's in the right form. Okay.
Did you plug my breakpoint?
So what is our tau p? It's still there, right? our tau p is s over, so let's see, I got 10 times 10 to the fifth. What's that? 10 to the sixth. And this guy is basically 10 to the minus 5 s plus 1, right? So our breakpoint is still at omega p equal to 1 over tau p equal to negative 10 to the minus 5, like that. Still in the same spot, okay? So if we look at this thing right here, right? So now I got this guy in the right form, okay? So what's my k value? 1 over 10 to the sixth, right? I got that. So it's 1 over 10 to the sixth, okay? I got my pole. So I got a 0 at 0. I got a pole at 10 to the fifth, okay? Now we're out of time for today, but basically when I move on, I'm going to go to step 3 and I'm going to say, all right, what I'm going to do is I'm going to plot the magnitudes of each one of those things individually and then add them up. So let's just do one of them, right? What's the easy one for us to do? If I have that 10 to the minus fifth s plus 1, what do I do for that? So 1 over, that's a pole at 10 to the fifth, right? So what do I do if I have a pole at 10 to the fifth? What do I do if I have a pole? I start with it at 0 dB, and then it goes down at what point? At 10 to the fifth, all right? So it starts flat and drops. If I had a 0, it would start flat and rise, okay? All right, I don't want to stop there if it were a bad stopping point, but that's my stopping point. All right, so we're gonna do probably a good 3 or 4 examples of this on Monday, right? We kind of got our frame of reference here today, all right, and then we're gonna work through a number of examples of this on Monday. All right, I might post a separate video of this particular one over the weekend for people that want to get started on the homework.